quicker than the fabric of spacetime can keep pace with it, and it will simply tear. I am apprehensive about this. Presently, our night sky is transforming rapidly, and in just a few decades, if not years, it may become entirely unrecognizable. Astronomers globally are raising the alarm. Specialists like Neil deGrasse Tyson have recently verified the imminent detonation of Polaris, and the story behind it is rather unsettling. Polaris, known as the North Star, has long been a constant in our night sky, serving as a vital reference point for stargazers, navigators, and astronomers. However, this may soon alter, changing our night sky and astronomical measurements indefinitely. Let's explore the significance of this threat and its consequences for all of us. Join us as we uncover the tale of Polaris as it nears its conclusion. For centuries, Polaris has directed mariners and astronomers alike, holding a revered status as a guiding light. Its steadfast presence in the night sky has been essential for navigation, but this stability may soon be disrupted. In September 2023, a research paper presented by the esteemed Royal Astronomical Society cast doubt on the fate of this celestial beacon. Polaris is on the verge of exploding, potentially disappearing from the night sky forever. Before we investigate the repercussions of this revelation, let's understand more about Polaris, also referred to as the North Star or Pole Star. Polaris is special due to its closeness to the celestial North Pole. Situated almost directly above Earth's North Pole, it appears nearly stationary in the northern sky. Found in the constellation Ursa Minor, or the Little Dipper, Polaris shines as a moderately bright yellow-white supergiant star, much larger and brighter than our Sun. It is not a solitary star but part of a complex triple star system, with Polaris A and Polaris B forming a binary pair, while Polaris B orbits around them. The interactions among these stars create gravitational forces shaping their orbits and affecting their behavior. Any disruptions in these interactions can lead to irregular variations in the star's brightness or pulsation patterns. However, the exact mechanisms behind these interactions remain uncertain. Polaris is situated approximately 323 light-years away from Earth, meaning the light we see from it today began its journey over 3 centuries ago. Thus, if Polaris were to explode now, we wouldn't observe it until over 3 centuries later. It's even possible that Polaris has already detonated, and we have yet to see the light from that occurrence. Throughout history, the North Star has held immense cultural, navigational, and symbolic importance. Its stability and fixed position made it an invaluable aid for ancient navigators, guiding them across seas and lands. Symbolically, Polaris represented constancy and guidance, remaining steadfast amid the ever-changing night sky. For astronomers, Polaris served as a crucial reference point, aiding in the study of celestial motions and variable stars. As a variable star, its periodic variations in brightness have provided valuable insights into stellar properties and the nature of variable stars. This characteristic also played a pivotal role in determining cosmic distances and calibrating instruments. These pulsations follow a predictable pattern, which has been the norm for the star, making it easy for us to anticipate its behavior. However, recently Polaris has deviated from this expected behavior. This irregularity in its pulsation cycle has perplexed astronomers, leading to a closer examination of this celestial anomaly. Instead of its usual predictable pattern, Polaris has started exhibiting erratic cycles of dimming and brightening. Scientists are now voicing concerns that the star may be nearing the end of its life. This aligns with behaviors typically observed in stars approaching their demise. The gradual elongation of Polaris's pulsation period, which was once stable, can be attributed to interactions within its star system. We've observed an annual increase in the pulsation duration of 4 to 5 seconds, which might seem minor but holds significant implications. Some astronomers suggest that gravitational interactions among the Polaris stars could be causing these fluctuations in its atmospheric conditions, directly impacting its pulsation patterns. However, others are more alarmed, believing that the star is on the brink of exploding. The similarities between Polaris's behavior and that of Betelgeuse, another notable star in the Orion constellation, are striking. Both stars have demonstrated perplexing irregularities in their luminosity, raising concerns about potential explosions. Stars in their twilight stages often display such irregularities before reaching the culmination of their life cycles. While NASA has expressed heightened concern about Betelgeuse, similar attention has not yet been officially directed toward Polaris. As a giant star approaches the end of its life cycle, it goes through various phases, including the main sequence phase, red giant phase, and ultimately the supernova explosion. Based on Polaris's irregular pulsations, scientists predict it has entered the stages of helium fusion, typical of giant stars nearing their end. These irregularities in Polaris's behavior align with patterns indicative of giant stars in their twilight phases, but definitive indications of its impending supernova remain inconclusive. Astronomers are diligently analyzing these irregularities to comprehend Polaris's fate. If Polaris were to go supernova, it would likely be a spectacular event in our sky, potentially outshining the moon and becoming one of the brightest objects visible for days, weeks, or even months. Its appearance might drastically change, temporarily altering our perception of familiar constellations like the Big Dipper or Ursa Minor, of which Polaris is a part. Rest assured, the Earth would likely be perfectly safe even if Polaris were to explode, given its mass and distance from us. While a Polaris explosion might not be as visually spectacular as that of Betelgeuse, it could still be visible to the naked eye for an extended period and outshine nearby stars. Astronomers and observatories would undoubtedly take note, sparking intrigue within the scientific community and among stargazers worldwide. However, the specific visibility and impact on Earth's atmosphere or surroundings would be less significant compared to a closer supernova event. But what about Polaris itself? What will be its fate after a potential supernova event? Let's clarify one thing. While massive stars typically conclude their lives with a supernova, this is unlikely to be the case with Polaris. When a substantial star goes supernova, a massive explosion occurs within it, marking the final cataclysmic stage in its life. This process involves a complete collapse of the core, triggering an intense shock wave that causes the star to explode violently. However, Polaris is not massive enough to undergo such an explosion. Instead, when Polaris exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transformation won't result in a supernova but rather a tranquil conclusion as it evolves into a small, extremely dense stellar remnant. A white dwarf is the remnant of a low or medium mass star that has exhausted its nuclear fuel. It's incredibly dense, about as massive as the Sun but compressed to the size of Earth. When this occurs, we will no longer be able to see its remnants from our planet, much like we observe the star today. Comparing the anticipated effects of Polaris's burst with historic supernova occurrences provides valuable insights into the evolution of stars and their ultimate fates. Comparing our expectations with well-documented supernovae like SN 1054 or SN 1987A, and more recent events such as SN 2011F and SN 2014J, provides valuable data for understanding the potential aftermath of Polaris's burst. For example, SN 1054 resulted in the formation of the Crab Nebula, a nebula that continues to expand and emit radiation across multiple wavelengths, offering astronomers a rich field for study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, provided insights into the processes of nucleosynthesis and the dynamics of supernova remnants. Analyzing phenomena such as the formation of nebulae, the release of cosmic rays, and variations in luminosity can offer insights into Polaris's unique characteristics. The creation of nebulae, such as the Crab Nebula, arises from the expulsion of material during a supernova explosion, which interacts with the surrounding interstellar gas and dust, enriching it with heavier elements and contributing to the cycle of stellar birth and demise. Furthermore, the emission of cosmic rays, high-energy particles accelerated by the shock wave of the supernova, has ramifications for astrophysical processes and environments of cosmic radiation. To conduct a definitive comparison, scientists assess variations in mass, composition, and velocity of expelled materials between the anticipated outburst of Polaris and other observed occurrences. This entails analyzing the light curves, spectra, and remnants from these events and projecting analogous characteristics for Polaris's expected eruption. Evaluating whether Polaris's explosion might result in the formation of nebulae or distinct elemental distributions enhances our comprehension of its potential outcomes. Another vital area of exploration involves assessing the pulsational variability of stars nearing their final stages, similar to Polaris, in comparison with observed supernovae or their precursors. This comparative study can help determine similarities or discrepancies and provide insights into the eruption mechanism. Pulsational variability in stars approaching the end of their life cycles may indicate internal instabilities or impending catastrophic events, offering clues to the evolutionary processes that lead to supernova explosions. Despite careful observations and thorough analysis, astronomers remain puzzled by the irregularities observed in Polaris's behavior. Unraveling the unique circumstances driving these anomalies is crucial for enhancing our understanding of stellar evolution. Comprehending the mechanisms responsible for Polaris's irregular pulsations necessitates interdisciplinary collaboration and the development of advanced theoretical models and observational techniques. The potential loss of Polaris as a significant reference point in the night sky raises considerable concerns for astronomical pursuits. Ground-based telescopes and celestial measurements would need recalibration, affecting the precision of astronomical evaluations. The absence of Polaris could also influence navigation systems and cultural practices reliant on celestial landmarks, emphasizing the importance of this cosmic event. The mysterious behavior displayed by Polaris underscores the necessity for deeper investigations and focused research efforts. Astronomers must navigate the complexities surrounding its irregular pulsations and provide clear answers, recognizing the significance of enhancing our understanding of celestial intricacies. Ultimately, the fate of Polaris remains uncertain, and only time will reveal its true nature. Nonetheless, the quest for knowledge and understanding amid cosmic uncertainty is a testament to humanity's enduring curiosity in unraveling the mysteries of the universe. The potential destiny of Polaris raises intriguing inquiries about the future of other celestial bodies. As we observe these transformations, astronomers are continually reminded of the dynamic character of the universe. Stars like Polaris and Betelgeuse are just two examples among the multitude of stars that experience dramatic changes, offering valuable insights into stellar evolution and the life cycles of massive entities. Beyond Polaris, numerous stars exist in comparable evolutionary phases. Some are in the later stages of their lives, exhibiting peculiar behaviors that could indicate imminent changes. For instance, several red giants show signs of instability, fluctuating brightness, and irregular pulsations. This variability can often act as a warning sign, suggesting that the star is depleting its fuel and nearing the end of its life cycle. Such stars become laboratories for astronomers investigating the mechanisms behind stellar evolution and explosion phenomena. In addition to examining individual stars, researchers also focus on star clusters, where multiple stars evolve together under similar conditions. Observing how these stars interact can illuminate the environmental factors shaping their life cycles. Clusters provide an excellent opportunity to study how gravitational forces and shared material can influence stellar behavior. The dynamics within these groups can lead to fascinating phenomena, such as the transfer of mass between stars, which may ultimately alter their evolutionary trajectories. Moreover, the study of supernovae, including the remnants they leave behind, offers a wealth of information about cosmic occurrences. When massive stars explode, they eject vast quantities of material into space, enriching the surrounding interstellar medium with heavy elements. These materials can contribute to the formation of new stars and planets, highlighting the interconnectedness of the universe. The remnants of supernovae often appear as nebulae, which serve as stellar nurseries where new stars are born. Observing these processes allows astronomers to piece together the cosmic puzzle of birth, death, and rebirth among celestial bodies. The consequences of stellar explosions extend beyond the immediate vicinity of the event. Supernovae can influence star formation rates in their neighborhoods, affecting the development of entire galaxies. The shock waves generated by these explosions can compress nearby gas clouds, triggering the birth of new stars. In this manner, the life cycle of a single star can have a ripple effect throughout the cosmos, shaping the evolution of galaxies over billions of years. As technology advances, astronomers are increasingly equipped to monitor and analyze these cosmic phenomena. Space telescopes and ground-based observatories utilize sophisticated instruments to capture detailed images and spectra of distant stars. Data from these observations assists scientists in creating models that simulate stellar evolution, enabling predictions about the behavior of stars like Polaris. Machine learning and artificial intelligence are also playing an expanding role in this field, allowing researchers to analyze extensive datasets more efficiently and uncover patterns that were previously overlooked. In addition to understanding the physical transformations within stars, the cultural impact of astronomical events should not be underestimated. Throughout history, celestial phenomena have influenced human culture, mythology, and navigation. The North Star, for instance, has been a symbol of guidance and hope for countless generations. As our comprehension of the cosmos evolves, so too does our appreciation for how these events shape our collective consciousness.